We want to essentially define what an eigenvalue eigenvector pair here is. Do notice that A does need to be a square matrix. I didn't mention that on the board, but yes, we only talk about eigenvalues and eigenvectors with square matrices. What does it mean? Essentially, give a definition to say lambda and V form an eigenvalue eigenvector pair for A. That's something to always keep in mind. Eigenvalues and eigenvectors always go together. It means A times V equals lambda times V. When that happens, for some non-zero vector V, it is essential that you say V is non-zero. I wrote the word non-zero. You could also write V is not equal to the zero vector. Then lambda, oops, not vector lambda, lambda and V form an eigenvalue eigenvector pair for A. That's all it means. What was the motivation for this? The motivation was we were seeking, maybe by exploring, it is good to do exploration in math, by exploring vector fields and with like stream plot in Mathematica, you happen to notice it does look like for many examples, there are solutions that are straight lines through the origin, either with the arrows pointing away, like it would be a source in that direction, or with the arrows pointing toward the origin, it would be a sink in that direction. But what does that really mean? It means when you plug a point on one of those lines into the vector field, take A times that vector, think of the point as being a vector, you get a scalar multiple of the original vector. It's parallel to the original vector, possibly pointing in the opposite direction. Lambda could be negative. That's the motivation. Second question was, why do we solve the characteristic polynomial to find eigenvalues? That's a little tricky. You got to take this equation and rearrange it by subtracting lambda v from both sides to write it like that. Then a little trick, another little trick, write lambda times v as lambda times IV, where I is the n by n identity matrix. Just a little trick. It's not obvious that that's a good idea. Take some experimentation. The first people to figure out eigenvalues and eigenvectors had to come up with this little trick to realize maybe this is a good thing to think about. I is the n by n identity matrix. I times v equals v, so I can make that replacement. Use the associative property. Rearrange the parentheses here like this. And then factor out a v. There's a common factor of v right here and right here. It can be factored out. That's a property of matrix vector addition when you're subtracting or adding things like this. It can be factored out. It's like a distributive property. These equations are all equivalent to each other. They all mean the exact same thing. And remember, we are after non-zero vectors for v. So that means we're also after non-zero vectors for v down here. You got a square matrix n by n times an n-dimensional vector giving you the zero vector. The only way you're going to have a non-trivial solution is if this matrix is non-invertible. The inverse of this doesn't exist if you want a non-trivial solution for v. Certainly there are trivial, the trivial solution works. No matter what your matrix A is and what lambda is, v equals 0 will be a trivial solution to this because it's a homogeneous equation. But we're after non-trivial solutions. So we need this matrix to be non-invertible. So we need its determinant to equal 0. That's why. This has non-zero solutions if and only if you've never seen this in a math class, if you write IFF, it means if and only if. It's mathematician's shorthand. If and only if the determinant of this matrix is 0, meaning the matrix is non-invertible. It's very special. We also call it singular. It's like a singularity. Kind of. Special. Rare. That's why we look for values of lambda that make this determinant equal to 0. And when you calculate this determinant, you've seen, at least in the 2 by 2 case, that you get a quadratic equation in lambda that you can use the quadratic formula for, or factor it if you're lucky. If A were 3 by 3, this would be a cubic, 3rd degree. If A were 4 by 4, it would be a quartic, 4th degree. If A were 5 by 5, it would be a quintic, 5th degree. Ugh. A is n by n, you get an nth degree polynomial equation, which in theory will always have at least one possibly complex number root. Though in practice, the roots can be very hard to find exactly. You can approximate them, but they're very difficult to find exactly. By the way, I've said this before, but maybe you forgot. If V is an eigenvector with corresponding eigenvalue lambda, any non-zero multiple of V will also be another eigenvector for that same value of lambda, for that same single eigenvalue. So always just finitely many eigenvalues, but there are infinitely many eigenvectors. However, for the purposes of solving differential equations, you typically, for each eigenvalue, you typically only need one eigenvector. It's good enough. That might make you think eigenvectors are always along straight lines to the origin and nothing else. That is often the case, most often the case, but we will see in a week or two that sometimes eigenvectors can occur for all vectors in a plane, 2-dimensional eigenspace it would be called, or even a 3-dimensional eigenspace, or even higher dimensions. When that happens, it's not so pleasant, but it's a reality that sometimes it happens. I also asked you to think about why this function, y of t equals e to the lambda t times v, where lambda v is an eigenvalue eigenvector pair for A. Why does this solve the differential equation dy dt equals A times y? I'm not even saying what A, lambda, and V are. You should be able to verify this in the abstract. Certainly in the reading, I'm pretty sure I did in the lectures, but I'm not positive. How do you do it? You got to check the left-hand side equals right-hand side. How? Differentiate. The left-hand side is the derivative. Find y prime of t. How? I don't know lambda. I don't know v. That's okay. They're constants. Lambda is a constant number and v is a constant vector. Use the chain rule. You'll get an extra factor of lambda. There's what the left-hand side simplifies to. What about the right-hand side? A times y. I got to replace y with this function. A times e to the lambda t times v. You can factor out the e to the lambda t. That's a property of a matrix times a vector written as a scalar times another vector. You can bring the scalar out in front. Those don't look the same, do they? Well, that's because you haven't used the fact that lambda and v are eigenvalue eigenvector pair. This is lambda times v. Now bring the scalar out in front. This becomes lambda e to the lambda t times v. We have a match. Left-hand side equals right-hand side. We are happy. Okay, you should be able to verify things in the abstract at this level of difficulty. But you need to understand what eigenvalues and eigenvectors are and believe you can do this while I'm telling you you can do this. And it does involve, properties of algebraic properties of matrix times vectors. By the way, there are other purely algebraic problems in a similar spirit you should be able to verify. For example, if lambda v is an eigenvalue eigenvector pair for A, you might wonder, what does that mean about eigenvalues and eigenvectors for, say, A squared? It's actually pretty important to know this. Is V an eigenvector for A squared? Well, what does A squared mean? It means A times A. By the associative property, that's A times AV. But if V is an eigenvector for the matrix A, that means there's a scalar lambda, so that I can replace A times V with lambda times V. And it's a property of algebra, then you can bring the lambda in front and write this. And I see A times V again. Use the fact that V is an eigenvector again. Write that. Use the associative property. That's a times there. It's not a dot product. Lambda is a scalar. You get lambda squared times V. What does this mean? It means if V is an eigenvector for the matrix A with eigenvalue lambda, then it's also an eigenvector for the matrix A squared with eigenvalue lambda squared. This is not an insignificant thing. It's actually pretty important. So it's going to be important for the matrix exponential. And you might guess that V would be an eigenvector for the matrix A cubed with eigenvalue lambda cubed. And if you did guess such a thing, you'd be right. And you could verify it in a very similar way. And in general, V will be an eigenvector for A to the nth power with eigenvalue lambda to the nth. Some things you should be able to do. I do sometimes put abstract things like this on exam 3.